The next speaker is Nilsson, and I want to say a few things about Martin because I know Martin very well. He has been doing his graduate work, his PhD work up in Chalmers in Sweden, and after that, Martin comes from high energy physics, particle physics, and switched to defected to complex systems in the middle of his graduate studies. And yeah, we need one of these pigtails. Does anybody have a pigtail for a Macintosh? No? Let me run and get one off here. Can you please, somebody tell a joke? I
mean, I guess I can start my talk without the smile. So I'm Martin Nilsson. So we just heard a talk on how cellular automata can be used to study self-replicating structures and can be very useful in that sense. I will try to convince you that cellular automata can also be used to simulate physical systems, namely, in my case, molecular self-assembly systems, which are important in the origin of life. I mean, it connects to the project that Steen was talking about yesterday. Yeah. So we're trying to simulate various aspects of the physical systems that are important for this project. And we're using cellular automata for that. I mean, cellular automata has traditionally been used to simulate physical systems. It started, I guess, with the molecular lattice gases, or lattice gases, where you try to simulate turbulence and the fluid dynamics with the lattice with the cellular automata. It's based on sort of the observation that the actual rules for turbulence only depends on conserving momentum in the collision between the molecules, between particles. So particles are moving and then they're colliding, and then you have a very simple rule for this collision. And then on the global scale, the dynamics then looks very similar to turbulence. And actually you can show that you get Navier-Stokes as on a macro scale from this micro dynamics. Okay, we have to.
We need to sorry about my strange stuff. So, I start with sort of a motivation for this work, and this is the slide that Steen showed the other day. And for those of you who did not see this, of course, it's very confusing to start here, but most of you were actually present at this presentation. So it's a sort of a picture on how we envision to build a self-replicating micro protocell. We have different components here. We have the lipid molecules, amphiphils, and we have these photosynthesizers, and we have the PNA molecule, which carries the information. And then by self-assembly, it folds into a structure, a little small protocell structure here, and then it
grows and then it self-divides over here. So we have a self-replicating cell. I will not go into the details at all, but just as the picture here motivates us to sort of ask questions. I mean, we would like to computationally address some questions relating to this. For example, I mean, there are lots of questions here on how this works. We're talking about problems, but we don't really know if this base pairing here will actually stay in this state or if it will dissolve, because it's important that, of course, that the strains will be able to be in different micelles afterwards, after this division here, in the blocks. And these are questions that, of course, you can go to the lab and try to see if this happens. But it would be good if you could address this question computationally and thereby guide the experiments to what type of systems we can expect this type of behavior to work and not work. And therefore, we're trying to develop a computational method which can address these questions.
Martin,
yeah.
What is PNA?
Well, PNA is it's a molecule that is similar to DNA and RNA, but it has a different backbone. Still, you might use a PNA sugar.
Yeah, it looks like a protein with a backbone instead of having phosphates and sugars like DNA has, and it's chemically it's simpler to make, and it has for our purpose the property it likes to stick to lipids. So we can for free, just due to the physics, we actually have a joining of the metabolic and the genetic materials.
And what is the P for?
It's peptide nucleic acid, and the man-made molecule.
So this means that in the self-assembly process here, we will naturally go into this lipid structure instead of staying out in the aqueous environment around. So this is a way to use the hydrophobic force to keep the structure in vicinity of each other. So that's why this PNA molecule is used. Okay, so there are various ways of trying to do computational work here. On the finest scale, I mean, on the really finest scale, we'd like to do quantum mechanics. But that is way too detailed to be able to address the self-assembly processes. So the level above, you can use molecular dynamics, which is essentially integrating Newtonian-like equations where you have all the atoms and then you have forces between them, and you integrate this system and can simulate some of these aspects. I mean, this has been used to simulate molecular self-assembly. The problem is that it's computationally very expensive, and essentially state-of-the-art here is that you can start with lipids that are rather close together, and then you can relax them into a little blob. And you can view that for a few picoseconds to see what happens if it's stable or not. But that's sort of the limit of what molecular dynamics can do. That doesn't really address our question, because we want them to grow, and we want them to self-divide, and we want molecules within these little blobs to diffuse PNA molecules and things like that. And on the high scale, you can do some Ginsberg-Landau type equation where you sort of use a PDE and you try to solve this. However, that does not include any detail of any kind of chemical interactions. It's very hard to interpret chemical interactions directly into these models. So we try to do something here in between to bridge this gap and address the questions that are most relevant for us. And therefore, we were going to use a lattice gas model, call it molecular dynamics lattice gas model. So it's essentially trying to keep as many details from the molecular dynamics as possible, but putting the dynamics on a lattice and thereby sort of stabilizing, making it's possible to run the dynamics much quicker on lattice because molecules don't come really close to a really high forces and keep them separate in that way. And therefore you can simulate much longer time scales than is possible with more traditional molecular dynamics.
Have you put order in it?
The order is explicitly included, however not shown in this picture. I'll come to the next slide. So this is one of the computations that the water is really important for the molecular self-assembly process. And actually simulating water molecules explicitly eats up most of your computational power. So this picture is not sort of a good picture of what's really going on. The lattice is almost filled with water molecules. And these are the lipids. They're sort of just 2% of the lattice computation.
Can I ask, what's the typical resolution we're working with?
So the resolution of the lattice, that would be sort of determined by a natural length scale determined by the water molecule, the hydrogen bonds between the water molecules. So it's 2.7 angstroms.
Okay, what's the angstroms?
So this lattice here is 40 lattice sites. 40. So it's sort of enough to include maybe one micelle at the most, maybe two. But it's not like a real, I mean, it's 1 or 2 micelles. So you essentially look at one micelle and see if you can divide it into 2 smaller ones and then you can form them. Yes.
You have periodic boundary conditions?
Yeah. This is periodic boundary conditions everywhere, so it's on a multi-dimensional curves. So okay, how do we do that? So it's important to include, of course, the conservation of the particles and the conservation of, in some sense, of total energy. And because from the direction here you get a potential energy, and then we use a continuous momentum to move the molecules on the lattice. We use a probabilistic update rule. So if I'm a particle at the lattice side, I also have a velocity, so I'm moving in one direction or another. And this we interpret with a continuous momentum, so we do a probabilistic update proportional to momentum in a certain direction. So the momentum space is continuous, whereas the spatial dimensions are discrete on the lattice. This is important to be able to have the kinetic energy to be interpreted in sort of a thermodynamically correct way. This is also different from a traditional lattice gas, where you usually only have one speed or a couple of discrete speeds in different direction velocities. And the potential energy table to actually simulate the interaction between the molecules, we use a potential here that includes dipole and dipole interaction, charge and hydrogen bonds, and some other weaker forces. And these are sort of the driving forces between the molecular self-assembly, together with the entropy, which of course comes from the different configurations that we can have on lattice. So the lattice structure is such that at each lattice point you can have a molecule, you can have a vacuum, and the molecules are different. I mean, here we have a water molecule. It has an internal structure. It has hydrogen bonds. The oxygen is giving out two possible hydrogen bonds, and it has hydrogen gives also hydrogen bonds. So two water molecules are residing close to each other. They would like to have a hydrogen pointing in this direction, meeting the oxygen here. So at each point, so the update step, we start by propagating force fields, or you field your neighbors and the local configuration. You rotate the water molecules, so they try to minimize their local configuration with respect to the internal structure. And then so moment manipulation is maybe that's for program for actually yes, for the program for a better word. Then we move and collide the molecules according to their momentum. And then also momentum is of course also exchanged in the collisions according to the hard sphere collision rules.
Sorry, what is the time step?
So a time step is in the cellular geometry. Well, this is a little bit complicated, right? Because you have to backtrack the time step in the sense that to make the temperature will give you an average velocity, and the velocity, the probabilistic update rule will tell you how the molecule that would be blown on the lattice would move over the lattice. And thereby you can sort of backtrack how long time step is. Because you're not really integrating Newtonian equations, you're doing discrete time step in the cellular automata. So you have to sort of interpret them backwards in a way. The time step here is physically it's about 10 to the minus 10 seconds. So I mean, the problem is that since I only have 15 minutes, it's hard to really go into the minor details of the rules here, so it shows you some results. But before the polymers are sort of extended objects on the lattice, right? So they occupy many lattices and have these bonds between them that they cannot break. So they move over the lattice according to the rules of not breaking these bonds, in addition to being collided by the background of water, etc. The results from the simulation shows here we have lipid molecules. This is the initial configuration. The blue or purple is water, the yellow is fat, and if you run this random initial configuration, you can see that you get this type of phase separation after a while in this picture. So it looks almost filled up. It's filled up to maybe 75%. So it's just a visual effect. It's hard to see the sides that are not occupied. So this is what you expect to happen if you have lipid molecules in a high concentration. Here is another simulation that is similar to this one, it's just a little larger than this. You can see that you have this phase separation with sort of strange forms going on. This is a very fluid state here. Now, if you use amphiphilic molecules, instead these fatty acids they only have hydrophobic monomers in them, like this. But if you put on a head group, which is hydrophilic, you get a different dynamics. It's not shown so clearly in this, but it will be shown in the next picture here. And that's where we expect to actually get micellation, small little dots, because they like to stick their head groups out of the water where the tails are hidden inside the little dot. And you start with an initial configuration that is completely random, and you run it for quite a long time. This actually takes 2.5 months on a PC to run. And you get one micelle here, and so it relaxes it down to one micelle, but this is sort of, due to thermal fluctuations, it actually self-divides here into 2 micelles, and then you can run it, and then later on it will again merge into one micelle and will go on like that. So this is a sort of steady state of this. You can show that on the simulation down here. So this is beginning up here, and then time step you can see down here. So we expect it to. So you see that it forms structures initially, and it's actually rather tricky here because you could easily conclude that this is the steady state and stop the simulation, because you can hardly see any change. But in fact, it is actually changing slowly towards this state where we have one micelle. This is the same here because we have the periodic boundary conditions. So remember that. And now we have one big blob. This is one micelle. And now it destabilizes and actually splits into two. No, I mean the picture is actually rotating compared to this one. And then it continues to evolve like this until they meet again, and then they sort of form this. So they form a steady state of well, oh, sorry. Okay, so this was, I mean, so there was a proof of principle that you can simulate this micellation process by molecular self-assembly. And we are currently trying to build in the PNA molecules explicitly. They are purple here, but it turns out that is slightly complicated due to the fact that the geometry of these, it's a little bit hard for them to move over the lattice, but we're working on trying to sort of have these systems work together. You can at least see that they are sort of sticking into these micellar structures and sort of residing inside the micelle like that.
You must need to have a lot of parameters in this instruction. How are they determined?
Yeah, I mean, the interaction strength, etc., are determined on basis of chemistry. I mean, we know what the strengths of the hydrogen bond compared to other parameters. So these are more or less just to look them up in the chemistry book.
But you're putting in much more than just that. You're putting in a whole molecule. Right? You're putting in water.
Yeah.
You can have the interaction of water to other.
Yeah, I mean, but you know the strengths of these interactions compared to each other. I mean, I agree that there are parameters, but you know approximately how strong these different forces should be compared to each other. And it turns out that the dynamics is rather robust to small changes in the parameters, which we hope for. The largest approximation is, of course, the fact that you are on the lattice, which means that you're not really the correct dynamics in the way that we expect. In a way that real molecules are moving, but the hope is, of course, that the general structure, the thermodynamics of the system is represented well enough to be able to address these questions.
You can check for some of these parameters by, for example, the vectorization tool based on your parameters and get about right within entries.
Yes.
So there's lots of internal checks you can do.
Yeah, we actually
It's been modeled to death at the moment.
Yeah, so we're working on, I mean, just to get the water to work like this, it will work. So I mean, you're trying to, for example, compare that to molecular dynamic simulation of water, and then you measure sort of various types of parameters, and if you have different densities, and what happens if you do that, this and that. So this is, I agree, of course, complicated, but we're trying to compare it to molecular dynamics and the forces, or sort of you look them up in the chemistry book and see what they should be, and then you hope for this to work in that way.
Using that Jones potentials.
Yeah.
That's good stuff.
And you hope, for example, to be able to capture in molecular dynamics, you know that Hodge space is different than you have Jones and then you have the walls. Yeah. You should be able to see the difference in pressure volume diagrams and different things like that. And if you can capture that, hope that this will also work in this sense.
Would the phase transitions for water out of this model?
Yeah, well, I mean, it's not really enough to really simulate phase transitions. This is simulating water in that sense. It's extremely complicated. We're not hoping to be able to do that. I mean, also due to the geometry constraint of the lattice, we don't have the right angles of the water molecules exactly. But of course, you hope that this is might not be tremendously important to make the self-assembly graph work correctly, right? I mean, the details of the water might not be important for this to work. I mean, of course, you can say what it is and then you can give up, but the hope is that it's not tremendously important to simulate all phases of the water to This is fluid water.
Last question. So in the stable state, at long time into a stable, we have 1 mice and 2 mice alternating,
Yeah.
and don't pick up more than that.
Oh, yeah, sometimes they do. I mean, this is just roughly. I mean, due to thermal vibrations, different things happen. You can see also that you have all these small things. I mean, there's question what you call the mice at all. I mean, so
Okay, so in principle, you get a state of all sizes.
yeah, yeah. I mean, you can sort of, actually, you can actually, yeah, that was another thing that we're working on to actually calculate the size distribution of mice cells can be derived into a probabilistic curve with a maximum, with an optimal size, and you have mice cells of all different sizes, and a tail for small things and for big things, and so it's more likely to be of a certain size, in a certain size range. This is what you observe in nature too, of course.
Would that depend on temperature? What distribution you get?
Oh yeah, it depends on the temperature, it depends on many different things, the pH and the length of the amphitheater volume that you're using, etc. And this is one of the parameters that you can check with experiments too, because the size of the mice cells should, of course, correspond to what you see in nature. And if you change the parameters, they change in the same way. Because this is also one of the things that experimenters have really been measuring a lot. Mice cell size distribution is important for many things, but in industry and where you have oils and where you have fat, and when you want to do things with this, it's important to know the size distribution.
So I think we've had a sort of completely continuous transition from the talking to a discussion. This is very good. So let's maybe we should say thank you. So if you are there any more questions here?
One question was, surface tension comes basically as a result of calculation, right? The other question is, what about waste products? There's no waste products in this simple approach, right? And all the cell material is assembled from the little stuff that has been somehow left out.
Yeah, I mean, this what I should here doesn't contain the self-replication. It's just one aspect, which is the method of self-assembly in the myself. Those are actually that sort of providing things. I mean, this is where we try to add a PNA motor. This is sort of the first step to try to include one of the other building blocks. The metabolism isn't included at all at this point. So we're trying to make these work and then build on more and more complex things. So the waste products are not there. It's just these things self-assembly to these structures. That's what you have to make that work before you add the other molecules onto this. Because it's sort of in this little thing that we hope will happen, supposed to happen.
So one last question.
Yeah, I have a very simple concept of fat and water, but when you have it in the kitchen, normally it separates very well, so you have fat on the top and the water below.
Yeah.
How do you bring these substances to mix in a way that you have it? When you start, you have an almost random distribution of water and fat.
Yeah. No, but what you see in the kitchen is a slightly different molecule, I think, than this. This is the heavy group here, and the tail means that they form the two mice. So if you have only, as we showed in the picture before, if you have only
this is actually oil, this one.
Yeah. This is oil, right? Yeah. And these show these types of structures where they actually separate quite well. Because we don't have gravity here, so it doesn't really, one does not lay on top of each other, but they separate completely. They do not form little blobs like the mice cells. But the thing changes when you have this little head group here on top, or if you put soap in water. So the soap sort of playing the role of the head group, put a little film on top of the blobs. That's why you put soap to get away with the fat. When you sort of so this is a different system. That's the
very good last question.
Is the problem with this isn't the fact that you have in the kitchen that is actually already some cells, whereas what you have here are the lipid molecules, and lipid molecules you can mix with water, but small lipid cells you cannot mix with water.
I mean, real fat and that we have is actually is a more complex molecule. It also has a head group. When it has two tail groups.
Yeah, but the reason that you can mix it with water is not the molecule itself, but it's and you start out with the molecules itself.
Yeah, that's right. So when you put butter or
it's a small block of
that's you already start out with some of the fat, so that it is already to
sort of start with your cells.
Yeah, that's right. Okay, let's go and have some.
Okay. Because of complicated scheduling conflicts, there are actually two meetings going on right now. And Martin is going to speak in both of them. So instead of asking him to speak twice, the people from the other meeting have come into here and here. So now we all have to leave for the rest of that meeting, but so just excuse the disturbance. I wish we could stay.
How's the big actually? So we are nice to see you. Everybody.
Yeah.
Yes, but now
Altså, der var en ting, som